Hello and welcome back. And we're working on the examples now, and we're looking at the continuous distribution. So the example I have here, I have a table that shows the months and the failure rates. One thing I don't like about this example, I'll point it out now, is that you'll notice that 6 months, 6 months, there's overlap, so you're not sure if something failed exactly on 6 months, why did it fail? But that's set aside for the moment, not really the focus of this example. We're using that table, and what they've done is they've recorded failure rates of their printer hardware. So in the first 0 to 6 months, if we look here, 4.5% of printers fail in the first 6 months, and then they've gone ahead and they've recorded the data accordingly. So first question here is to construct a continuous distribution for the graph. Now for this, when you're answering that question, you can just do a rough sketch going by hand here. I've already used the graphing calculator. I input that information to the graphing calculator already, so this is what resulted. So just using a quick scale here, and when I look at the data, and if I connect it with a smooth curve, and you can use graphing software or whatever you're going to use, what I find here with the data, so this is A, the graph, and I'm really moving on to answer B now. What is the resulting distribution? So I'm really looking at this curve, and if I extend the curve out in both directions, and what I find is I end up with what appears to be a hump here, and I also find a hump there. So we have 2 humps, which would mean that if you have more than one hump, in this case 2, we have a bimodal distribution. So the data is a bimodal distribution, which means that the data could be, if you want to have significant results here, we should be looking at it in two sections, but that comes when we talk about that later on. So this is bimodal distribution. So on the C part, why do you think the printer failure rate would have this distribution? Well, and this is where you take a step back. There's no mathematical answer. This is real life or practical experience. What you're going to find with technology, so with technology, it either fails immediately. Oh, I don't know on the spelling on that. We'll keep it for now. Immediately, and that could be because of factory defect, shipping. So if you have a piece of technology, it's going to fail out of the box 4.5% of the time because of those listed there. It's either going to be a factory defect, something wasn't put together right, it was damaged during the shipping process, or it fails over time due to wear, age, dust, whatever other factors contribute to the failure of a piece of technology, especially a printer. So that wear and tear shows that over time we start getting a higher failure rate as we move into a longer lifespan. All right, we see that at roughly 3 to 4 years here. That's when the failure rate really goes up for printers, which makes sense. They're only built for a certain lifespan. So D parts calculate the mean and use that result to discuss the distribution. So I'm going to pause here for a second, calculating the mean average of the failure rate, and we'll have that discussion. Okay, and over that first, the 8 segments there, so for D part, find X bar is approximately equal to 3.1%. So when I go back to my graph here, 3.1%, if each of these on the scale represents a 1, so 1, 2, 3, so roughly here, that's the 3.1%. So we find that the mean could be located here, or could be located over here. So what we end up with when you have a bimodal distribution, you end up with 2 possible mean locations. So the fact the location of the mean occurs in two locations supports our initial analysis of a bimodal distribution. So it's just supporting evidence for us. All right. And finally, what are we on? E part, determine the equation to model this trend. So really what you need to do is you need to use technology at this point. And that's why I plugged it into the graphing calculator. So if I bring up my little graphing calculator, you can see my data here. So when I'm looking at the graph itself, I know that it has to have a low point, has to go up. So what are we talking about in terms of possible regressions? Well, we go to Stat, Calculate. I know it's not number 4, it's not a line. Could it be a parabola? We can check. When we look at a quadratic or a parabola, my r squared is 0.94. And if I go back, it could be a cubic, could be a polynomial, could be a cubic. So I got to beat that 0.94 under the r squared. And now my r squared, if I use a cubic regression, is 0.985. I want to go back because also a quartic, a fourth order function, would also get that. We talked about that in the previous unit. So with the quartic, try that r squared, 0.985, and 0.9, oops, that's not the r squared term, 0.99. So it almost fits the quartic exactly. So what I want to do then is I'm going to take a screenshot of that, oops, and bring that forward, put it into my note. So we will bring that in, and I said the r squared value is 0.99. So just finishing that off, bring that down a little bit, so you can always copy this down into your note. So for E, it's a quartic. And for people that can't remember, the quartic is that W shape or the M shape, depending on direction of opening. And the formula for it would be y equals, and there are our values there. So 0.009 x to the fourth minus 0.195 x cubed plus 1.73 x squared minus 6.3 x plus 9.3, where y equals, so the y values are the percentage failure. Oops, not y equals, y represents, sorry. Y represents percentage failure. And x represents our time in months. And our r squared is equal to 0.99. So therefore, our model, therefore, we have a very strong model. All right. So that kind of combines a couple of questions that you'll see in the homework all into one question here. And like I said, in this case, graphing calculator seems to be a little bit more efficient than the other software that's out there since we don't have access to Excel. Last example, looking at driving time between Mitchell and Windsor is found to be between 195 and 240 minutes. So determine the probability that the drive will take less than 210. So this is a uniform distribution, and the reason is it's because the driving time you're going to get there successfully, and the range is 195 and 240. So if I give myself an XY axis, on here is time, on here is probability, and I know that I'm going to get to Windsor between 195 and 240 minutes. So I know that the probability of me arriving at Windsor, so probability of arriving is 100%. So remember I talked about probability density. Now we're looking at the area under the graph. So our probability graph is going to look like this. And what we want to do is find the area under the graph. And since we arrive between 195 and 240, that is where it needs to give us that percentage, that 100%. So we know that our area in there is our 100%. So when you're dealing with this uniform distribution, to find the y value on the y-axis, you need to do 1 divided by our range. So 240 minus 195. And when you do that division, you get 0.022. So that is the value of our y-axis. So the question wants us to determine the probability, x is our independent variable, that it will take less than 210 minutes. And I'm going to put area. And the area here, 210, occurs about here. So what's the probability that's going to be 210 or less? Well, this is the area that we need to calculate in order to solve this particular question. So our area, since it's a rectangle, is length times width. So we know that the length, or the base here, from there to there, is going to be 210, multiplied by our width, which is the 0.022. And when we do that calculation, 210 times 0.022, we get 4.62. And that is above 100%, which is, oops, not what we want, because my mistake here, I forgot that it's 195 is the quickest it's been done. So sorry, it's the area. Our area only extends to 195. So my mistake there. So it should be from 210 take away 195 is the length of the rectangle. So it's this rectangle here we're looking for, multiplied by 0.022. So trying that, 210 minus the 195 times the 0.0, and we get 0.33. So therefore, probability is 33%. It will take 210 minutes or less. All right. And we're going to talk about what happens if it's not a rectangle in a future lesson. There's the homework at the bottom. So when you're doing this, it's uniform distribution, and you'll see a couple in the homework. And like I said, the tricky part is A, finding on the y-axis the value of the top of the rectangle, and B, don't do like I did. Remember that 195 is the minimum travel time. You can't get there in less than 195, or so it's recorded. So you got to make sure that you're only finding the area of this rectangle right here. Okay? You're not going outside that. All right? If you have any questions with the homework, you know where to find me. Good luck.